The next section is about sample proportions. So we're going to start with the central limit theorem. And the central limit theorem says that if you take many large samples that measure the same thing, for example, if you're measuring a mean, the sampling distribution of the means will be approximately normal. So this is going to apply for almost everything that we're continuing to do in the class. That if your sample size is large enough, then what's going to happen is your data will follow a normal model. Make sure, by the way, that you put that word approximately in there. If you just say that it is normal, you will, believe it or not, you'll lose points for that because it's not going to be exactly normal. You have to use a qualifying word like approximately or roughly normal or fairly normal. So the central limit theorem is kind of hard to understand, but the implications of it are very, very important. So it will come up again and again, but you might not realize that it comes up again and again. We also usually often refer to it as a CLT. So if you hear that, just know that that's a central limit theorem. So now I'd like to go through some important notation that you're going to see a lot. And I think you've seen most of these before, especially the first four, but you haven't realized what the difference between some of them is. So for the population mean, we generally will use the Greek letter mu. And one little trick is that population parameters usually involve Greek letters. There's one small exception, which I'll talk about in just a minute, but population parameters almost always involve Greek letters. The sample mean is usually denoted by x bar, x with a bar over it. Occasionally you'll see it as y with a bar over it, but usually it's x bar. The population standard deviation is the Greek letter sigma. The sample standard deviation we usually write as S. Sometimes you'll see it as S with a subscript of X, but usually it's just an S. On your calculator, though, it does use it as S with a subscript of X. The population proportion is P. This is actually our one exception to the rule of population parameters using Greek letters. And actually, you sometimes will see this written with a pi. There are some books that actually denote it by pi. Unfortunately, in math, pi is used for other things, so we usually don't use pi here. But if you want to do it with pi, you're welcome to. The last thing we have is our sample proportion p hat. So that one, just make sure you know the difference between the regular p and the p hat. So we have two formulas. The first one is the standard deviation for a proportion of successes, and that one is going to be the square root of your population proportion times 1 minus p over n, your sample size. And then the last thing, this is actually going to be more in section 7.3. The standard deviation of a sample mean is going to be your population standard deviation over the square root of n. So we're going to start with an example. We know that of all the cars on a certain interstate, 80% exceed the speed limit. We are going to use the 6895 99.7 rule, which, remember, is the normal distribution. To draw and label the distribution of the proportion of the cars the police will observe among the first 50 drivers. So this one may not seem completely obvious right away. What we are going to be doing is we are going to be drawing a normal model. We're allowed to draw a normal model because, well, we'll check some conditions to make sure that we can. But you'll notice the sample size of 50 is pretty high. Usually we're looking for something at 30 or more, but I'll actually talk about the actual size it needs to be before we use the normal model in just a sec. So before you actually can do anything with this, you have to check conditions. And from here on out, almost everything you're going to do is going to start with checking conditions. So we have 4 conditions. However, numbers 1 and 2, we usually group together. So the first thing you're going to be looking for is whether or not you have a random sample. If there's a random sample, then the first 2 are automatically satisfied. In this case, unfortunately, they don't tell us it's a random sample. So in that case, we're going to override that by using the independence assumption. So what we can say, they tell us that we look at the first 50 drivers. However, we are going to make the assumption that all cars are independent of each other. So what I mean by that is that we don't have any cars that are like following each other or anything like that. That would, we're assuming that that doesn't happen here. Now, rather than using the independent assumption, if the independence thing is weird for you, you can actually, we don't have a random sample, but what you can do is you can talk about the randomization condition. You have 2 options here. The first one was the independent assumption. You can say something along the lines of, this is not a random sample. But it's reasonable to assume that these cars are representative of all cars on the interstate. So either of those 2 options is fine. Now, if, I think I said this already, but I think it bears repeating. If they tell you that they took a random sample, then you just say this is a random sample and you're done. You don't have to say anything other than that. Okay, so that's our first condition, or our first 2 conditions. The next thing you have to check is called the 10% condition. And this needs to be satisfied in order to use the standard deviation formula that we're going to use in just a minute. And all we're going to say is, you think about how many possible drivers on the interstate. Our sample size of 50 is less than 10% of all drivers. So that's, there's an alternative way to write that. So our sample size of 50, if you were to multiply that by 10, that would be the limit of the population that we wanted. So you can also say there are more than 50 times 10 or 500 drivers total. So the basic thing here is that we're looking for our sample size to be less than 10% of the population. And this is something necessary to use in order to use the standard deviation formula. And we'll talk about the standard deviation formula in just a sec. Okay, the last condition, and you're going to use this for every single thing where you have a proportion. It's called the success failure. And the success failure condition is, it's listed as NP and N times 1 minus P. Both of these must be greater than or equal to 10. So in this case, they tell us the N, it's 50. The P is actually the population proportion, which is this 80%. So what you're going to do is you're going to do 50 times 80%, which gives you 40. And you're also going to do 50 times 20%, and that's going to give you 10. So in this case, you can't just write this, you have to write a little bit more than that. And you're going to have to say something along the lines of, since both of these are greater than or equal to 10, the success-failure condition is satisfied. And what the success-failure does is it tells us that our sample size is large enough to use a normal model. So this is a very important one to check. You can't just automatically use the normal model without checking this. It says large enough n to use the normal model, by the way. Didn't come in very well. Okay, so then the last thing that we're going to do is we are going to, so we did a lot of stuff in the beginning, but this is necessary stuff. You have to do this every time. The good thing is that it goes faster every time you do it as you get used to it. So now they're actually asking us to use the normal model rule to draw and label the distribution. If you remember the very first time we learned normal model, we started off by drawing things. We're going to do that here. So my mean is always going to be my population proportion, which is going to be 0.8 or 80%. My standard deviation, that's where we're going to use the formula on the previous slide. The formula was p times 1 minus p over n. Actually, as a little hint, if you notice that you have a percent but no standard deviation, you're almost always going to be using this formula. So you're going to get 0.8 times 0.2 over 50. Take the square root of that entire thing, which gives you 0.057. So now I'm actually going to do the problem that I need to do. So the problem is asking you to draw and label the distribution. So I'm going to draw a normal model. And my mean is going to be the 0.8, 80%. My standard deviation is 0.057, so I'm going to go up a standard deviation and down a standard deviation by subtracting. And you're going to do the same thing out to 3 standard deviations. The good thing on this one is they actually told you the percentages in case you forgot. So don't forget the labeling part. This first one, remember, is 68%, 1 standard deviation away. The next one is 95%, which is 2 standard deviations away. And the last one is 99.7%. I'm going to write that in another color because you might not be able to see it. And then the other thing is please, please, please give your graph a title. So I'm going to say proportion of speeders in 50 cars. And this right here, this box is my actual answer. However, if you do any sort of free response like this, you have to show how you got the mean, you have to show how you got the standard deviation, and you have to check these conditions. It's very important. Okay, so this next problem is going to be most similar to something that you would actually see. I think probably some people will get confused because they do mention that you are looking for a probability, but usually if you have a very big sample size, you can use a normal model. So what we're going to do is we are going to run through the process that we just did on the previous thing, but we're actually going to solve this out. So I'm going to start by doing my conditions. And so first of all, I'm going to be looking at the random sample condition. Now, it's not a random sample because we just have one bag. However, you can say, so I'm going to say this is not a random sample. but we can assume that this bag of M&Ms is representative of all M&Ms. So that's my first condition. My second condition is going to be the 10% condition, and I'm going to say that 250 is less than 10% of all M&Ms. And my last condition is the success failure. So my N is 250. My P, actually, in this case, is 0.3. This 0.25, this 25%, that is my P hat. That is my sample proportion. So when you do the success failure, you will want to use the population proportion. So just be really careful about that. So NP is going to be 250 times 0.3. And 1 minus P is going to be 250 times 0.7. And both of these are greater than or equal to 10. So I'm happy about that. That's satisfied. So all conditions are satisfied. Sometimes I like to say, like, all conditions satisfied. You don't have to write that, but it won't hurt. And I'm going to say use a normal distribution with a mean of that population proportion 0.3 and a standard deviation of 0.3 times 0.7 over my N, which is 250, and that gives me 0.029. Now, rather than writing out that whole thing, what you can do, I'm not sure if you have seen this before, but you can also say use N, that means normal model, of 0.3, 0.029. That also is a way to show that you're using a normal model. Just make sure that you show the work as to how you got that 0.029, but you're welcome to do that. So I'm going to draw a quick sketch. You do not need to draw the elaborate one that you did in the previous one. And we're going to start, it looks like this. So now from here, you're actually just going to be doing you're just going to be doing the stuff that you have done in the past. So we're going to be finding the probability that P hat, our sample proportion, is greater than or equal to 0.25. Now on this part, be really careful with notation. If you were to put P here, you would lose a half a point or something like that. So P hat is what we're looking for. We're looking for the probability our sample proportion is greater than or equal to 0.25. If you are not sure that if you're going to do the notation correct, it's almost better to not use it at all. I know that sounds silly. Like I do like it when people try to use the proper notation, but on the AP test, they actually will mark you off if you use the wrong notation here. So when you do that, you're going to use your calculator, and you are going to use normal CDF. And you are going to start, your starting value is 0.25, that's your lower. Upper value is any big number. Your mean is 0.3, and your standard deviation is 0.029. When you do that, you end up getting 0.957, and that is your answer.